Hello, welcome again to this channel. Let us study a healthy balance system. To be able to have this one, first it should have a three-phase voltage equal in magnitude. So we are referring here to a three-phase system. It means that your V sub A for the voltage, for example, your voltage at phase A is V sub A, and for phase B, B sub B, and for your phase C is B sub C. And the voltage that the magnitude of each one should be equal. For B sub A, for instance, this is equal to the Vm, or the maximum voltage or the peak voltage, cosine multiplied to cosine omega t. Okay, this is for the time, and omega here is actually, this is twice the pi times the frequency, okay, 2 pi. And for B sub B, it should be V sub m cosine omega t, okay, minus 120 degree. So you have now here an equal magnitude, Vm and Vm for B sub A and B sub B and B sub C. Also same as that one, it is just multiplied to cosine omega t plus 120 degree. So this meets the first requirement for a balanced system. The second one is that these three phases, namely BA, VB, BC, are shifted from each other 120 degrees. So you'll notice here that the angle of B sub A is 0 degree, and the second one is 240 degree, and B sub C is 120 degree. One rotation gives us 360 degree, and 360 is divided by 3, that will be 120 degrees. So this phase voltages, okay, are 120 degree shifted in each voltages. Okay, that is the second requirement. For the third one, the three-phase currents are equal also in magnitude. So if you're going to get the current of this one, let's say that is IA, and for the current of B sub B is IB, and for the current of B sub C is IC. So it should have also equal in magnitude, referring to the peak value of the currents multiplied to the cosine omega t. Okay, so it should be equal also, but you should have a balanced three-phase load, for it will equally be, the current will be supplying equally to the balanced load. But if your load is not balanced, you can expect that IA, IB, and IC's magnitude will not be balanced also. And for this three-phase current, so it has also 120 degree shifting, but there is also another, what we call the phase shift angle, that will be introduced to each of these currents in the phase of our phase currents. So it is shifted by a shift angle, plus the 120 degree which is present there. This is how you have a healthy balance system. But for further discussion, you see here a picture of a rotating coil cutting the fluxes on a permanent magnet, which is north and south. So the magnetic flux is going from north to the south, and when this rotates, the coil cuts it. This gives us an induced voltage, giving us a sinusoidal waveform. For the first half of rotation, it will be positive, and for the second half, it will be negative. Actually, to be able for us to have the induced voltage, or E, now we have this formula of negative N, okay, the number of coil multiplied by the variation of the fluxes with respect to the time. You can use here P or phi, theta or phi, so I am using here, but you can use also phi, for fluxes. So this is for the flux, and T here is for the time, and this one, this N, is actually for the coil, number of turn. So if you know this one and the fluxes with respect to time, okay, so it will also, when we talk about the time, so we will consider also the speed of rotation per unit time. and you multiply that and you can have your EMF value. So this is a figure for a rotating coil. Now I am giving you here another example. This one is a figure of a generator giving us a single phase. This one is for a two-phase, and this one is for a three-phase system. Now here, quite different from the previous picture that you have seen, because the one that is rotating here is the magnet and your coil is stationary. So this is how you produce a single phase, the same as what you have seen earlier. So if your coil is, subject to the magnetic flux of the north here, for instance, okay, so this is your north and this is the south here. So the coil here is in maximum value. The induced voltage the coil is taking here is at maximum. This is that point. So when it moves here, it goes down up to the horizontal position. This is now your north, this is your south of this magnet, and since it is in horizontal position, the coil will be at the minimum. Actually, that is, there is no cutting of flux here, so that will be here, 0. So when it removes, going here, it is now facing here, north. So this is now the negative peak, and it goes again back to here, so to 0. So this is what we call the one cycle. So if you have a 60 cycle per second, this is what we call 60 hertz. We don't write any more cycle per second, but we write hertz. It just means that there are 60 times of this rotation per second. This is for the single phase. For the two phase, you just add another coil here, which is for B. So you'll just observe, if this is your magnet, this is your north, and this is your south. At this point, the maximum here is for A, and your B here is at 0. So you'll notice that this will go down and this will go up to this point where it is in horizontal location. So your peak now here is at B, and A is at 0, and again it will be on the negative cycle. So if you're considering a three-phase system, you just add coil here. The coil intended for phase A, and for this one, the red color is for phase B. For blue one, this is for phase C. So again, if you will observe, it will be, you'll notice that the phase is when the other one is at peak, the other one is at a certain point here, and where it intersect here. So two phase, you'll notice that the peak A and B, if you'll measure this angle here, we call this a shift, it is at 90 degree. But if you have three phases for coil A, B, and C, you'll notice that the shifting here is at 120 degree. So we can also represent this in a vector form using arrow. So here it is represented by a sinusoidal waveform, and for the A, for phase A, we use the straight arrow going to the right, and this is for the B, the phase, and for this one is C. So this is shifted or equally divided into 360 is divided by 3, which is 120 degree. You can also use color notation, which is for the phase A is red, for the phase B yellow, and for the phase C that's blue. Three phase. Okay, the direction of rotation is counterclockwise. So here in radian per second. So this is how you present it in phase voltages using trigonometric function. So again, VAN, you can further understand this by having this one actually. So we have this one, Okay, so this is inductor. Okay, so this is star connection, star connected. Suppose this is your A and this is your B, this is your C. The point of action of the coil on each side here is what we call N, or the neutral. Be able for us to have VAN, we are actually referring to this point A up to here. So that is Vmax cosine omega t. And for your VVN, that is this one, V to this point. Cn is C to N. This is how you represent it using here trigonometric function. And you can also write it in a symbol here. Use this one. Some other professor pronounced this as CIS, CIS, abbreviation for cosine I sine. Okay, some other professor used as an angle. So BAN is angle, BCN is angle 120 degrees. So your VAN is cis of 0 or angle 0. And your VVN is cis of negative 120 degree or angle negative 120 degree. And your BCN is cis of 120 degree. So this is for your phase voltage. Okay, now for the line voltages, no? So let's again draw star connected inductor or system. So again, this is your A, this is your B, and this is your C. So this is your N. So able for us to have VAB. See here that VAB voltage here is actually composed of by having the Kirchhoff's voltage law, VAN here, VAN plus V and B, B and B. So we have the value for VAN. So we know that that is B phase angle cis of 0 plus BP, the peak voltage cis of 60 degrees. So you have to know where did this came from. Actually, your V and B, which is the B max or BP value, okay, this is actually negative of BP angle or cis of negative 120 degree. Okay, so do you remember that? Because our BVN is actually B peak cis of negative 120 degree. So if you are going to change this terminal, you will introduce here a negative sign. Now if we are going to have BAB, for instance, BAB, so this is now, so the one that is using here B, we use B peak, so B peak cis of 0 degree, this is for BAN, as so it will be BNB plus BNB, so that will be B peak cis of negative 120 degree. Okay, so what we're going to do is, how do we get this 60 degree? It just turn to be B sub P. I'm just copying it, cis of 0 degree. So if I'm going to remove this and make this positive plus B peak, I will add at 20 degree an angle of 180 degree here. You just remember this one. If you are going to make this positive, you just add 180 degrees. So what is the result? The result will be B peak cis of 0 degree plus B peak. This is now 120 negative plus 180, so that will be cis of 60 degree. Now for further simplification, you'll find that BAB is actually to the square root of 30 degree. Now it is common also to, this process is common to BBC and B sub CA. How long is your B phase compared to the V line? So you call this BAB, BBC, BCA as voltage line, line to line voltage line. So how long is that? Line is actually equal to the square root of 3 times the B phase. So if you have here, if you're consider this representation, this is your BAN, BBN, BCN, the phase voltage. So this is now your V line. So you'll notice that it is represented here that it is much longer than the phase voltage. Okay, and you will notice that it has a voltage leads the phase voltage by 30 degree. So you have here 30 degree, here 30 degree, and 30 degrees. So it represented here. So if you make BAN a C sub 0, so that will be a 30 degrees here, B sub AB. So you can use to be able to get a square root of 3 here, you can use the cosine law. So we are here actually a triangle in which here here with the 30 degree, and these are the things that you should know to be able for you to have a healthy balance system. So this is the relationship of the line voltage to the phase voltage. So you multiply by square root of 3 the phase voltage to be able for you to get the line voltage. In the representation here, so you'll find here, you'll see here, instead of using A, B, and C, we use here VR and Y and V. So this stands for the color, this is for the red, this is for yellow, and this is for the blue. Okay, you have the voltage here, RY. So again, you have a angle here, angle shift. There is an angle here which is generated also from the balance load. So you can find this using the balance load. So notice that in reference with the voltage, you have here a phi angle. Okay. Again, here in the bottom, I use now here ABC. So here AN, BN, CN for the phase voltages. So you have the PP here for H cosine omega t, and for the phase current, which is lagging by theta, so you just subtract in each of the angle of your trigonometric function cosine. So you just subtract here negative theta. This will be your current. Okay, notice the difference between the two. This is for the voltage and this is for the current. Here the more representation of a healthy balanced system. So you'll notice here that this is for the load. For the resistance of the load is on the horizontal line, and for the inductor or the capacitor, that will be the vertical. So here our Z, or the impedance, this is Z squared, but you are only getting Z here, so you take the square root to both sides, so you have here R squared. This is for the resistance, and for the inductance and capacitance, you just subtract that one and have it squared. Get the phi here, you just apply trigonometric function. So you have here the voltage for your inductor, which is IXL, the current that is flowing here, multiplied by the XL, and for the voltage for the capacitor, the current that flows here times the XC, or the capacitive reactance, and for the voltage of the resistance here, you just multiply the current with the resistance. The inductive capacitance is always equal to 1 over omega C, and for the inductance, omega L. To get the phase, you just subtract the inductive reactance to the capacitive reactance divided by the resistance and get the inverse tangent of that. So you'll find this one, phi. So you can also use this one, for our relationship with the power, because power is also represented in a right triangle. So this phi here actually is the phi for your power. So you know that this one, so this is for the resistance, this is also for the real power, or the P. Okay, the real power. this as real power. Okay, this part, the vertical one, for our inductance and the capacitance, I mean inductive reactance or capacitance, we use here Q. So this is what we call the reactive power. Okay, so for this one, in which you see everything, the power for the resistance and for the reactive power, we represent it by S. Actually, we call this as the apparent power. Apparent. So that will be your impedance here. Okay, so you can easily get the phi here by using your load. Okay, so you'll have here the real power, in which the unit is watts, and for the reactive power we use here volt ampere. Reactive, here we use here VA or volt ampere. You can also get the power factor here. The power factor is actually the cosine of this one, of this phi. Okay, cosine of this phi. Or if you know the real power, you just divide it by the apparent power. That will be the power factor. So easy to get the angle, no, between the powers, the three different kinds of powers, and also for the load, for the resistance, the inductive reactances or the reactances, and for the impedances. So this is how you have a healthy balanced load. Thank you.